Ladies and gentlemen, good morning. I'm happy to greet you on the problem-solving session of the course of Advanced Quantum Mechanics. We will do supervised homework today. Before starting with the real stuff, let me take a second and congratulate ladies on occasion of International Women's Day, which is today, and which is celebrated for 100 years. Right, it's not very well spread in the Netherlands to celebrate it, but nevertheless, people are aware of this. So please receive my sincere congratulations. Good. What would be our work way for today? It is supervised homework, so you're supposed to concentrate on homework today. I will explain the formulations of the problem. I will start with problem 1. Then, for some time, we will work on problem 1. I will record only explanations because the rest of the session it doesn't make sense to record. Right. So after I've explained, and during explanation, you, of course, ask questions as usual in the chat. After explanation is over, we will be answering your individual questions. The way is the following. You raise your hand in Zoom, okay? Then an instructor will contact you. Instructor, we will write in the common chat, okay, I will take care of the question of, I don't know, Bill, Art, John. Fine. And then this instructor comes to individual chat with you. You formulate the question and you get the answer in individual chat. In this way, all 4 instructors can kind of serve you simultaneously. Right. If an instructor finds that your question is interesting for everybody, one of the typical reasons if the question, kind of the same question is asked 2 times by independent people, of course, it's a big chance that it is interesting for everybody. Right. In this case, an instructor just talk about this with voice and explain the question and the answer for everybody. So that's perhaps not an ideal work way. I'd prefer break rooms, but for some reasons it's not that convenient to organize such break rooms in Zoom and make sure that it's really efficient. So we will do in this rather primitive manner. Any questions about the manner we work? I hope I'm not muted. It doesn't seem so. Everything is clear. Fine. Then let me talk about problem number 1. I just go to Brightspace, and you see the problem as it stands at the Brightspace. Good. So let me go point by point. First, the common formulation. Any one particular operator, a hat, can be written using correlation and annihilation operators S. And what you find here, you find operator, uh, summation over indices ij. You find a number, whatever you might call it, tensor, if you want, doesn't matter. Something with two indices, a number with two indices, which is given, right? And then you find operators, creation and annihilation. Good. That's about operator A, and then it's two-particle emission operator, which looks a bit longer. But you see the structure is about the same. There is whatever, let's call it tensor, which depends on four indices. And two creation operators, two annihilation operators all have indices. Good. What follows is a typical structure, typical for all homework problems, and typical for examination problem. Let's see what kind of structure it is. Here we find 4 points, which kind of compulsory, and single bonds point. It is clearly indicated that it's bonus. You don't have to do this, but if you do, you get extra score points. In this case, 75 points. Each normal point from A to D, each normal point costs 5 points. Right. Then you understand that you should really think of your time schedule before trying to do something on the last point. It requires quite some time, much more than the rest of this particular homework. Good. So let me go through the points. And again, if the question is not clear, it's better to ask about it in chat now. It would be efficient. Explain symmetry properties of the object B, I, J, K, L with respect to index exchanges, separately for bosons and fermions, and with respect to complex conjugation. Yes, Margit. A and D are all by 5 points. So in total, if you don't do bonus point, you require 20 score points for this first homework task. And then it would be 60 points for the whole homework of the first package. Good. Point A. Let me just immediately say how to do this. You just, it is a bit of automatic rewriting of this expression. Since there's a summation, you can easily switch indices without changing the summation. But here, operators somehow change. And you can compensate for this change replacing the operators. Okay? Using commutation relations. Then you get symmetry relations for this B. Complex conjugation works in a bit the same way. In this case, it's important that the operator is Hemisian. So what you do, you write it as you apply Hemisian conjugation to this and to this, so that becomes complex conjugated. Something happens with operators, you know how to do this. And you sort operators in the same way, you got symmetry relations. That was point A. And it's also good to notice that points usually increase in the level of complexity. So A is supposed to be a very simple point. There's very little to compute, right? Then point B, this is a little bit more tedious computation. I wouldn't say even say tedious, but anyway, it is simple but a calculation. Right. Then point C, then you really have to work. Write down this and this for fermions, for bosons, subtract them, and say something about the way you see the results. Good. Then point D, it also requires calculations, a length, or rather lengthy calculation. And finally, point E, which requires almost infinite size calculation. Good. In principle, I have finished discussing the problem formulation. Any questions? Otherwise, we will switch to individual questions. I don't see the questions. Bonus 75 points. Yes, for this particular problem, the bonus is 75 points. It can be 7 points, it can be 15 points, it depends on the problem. It is, if no typos, it's just as it is written in the problem formulation. Should not it be 7.5 if the rest are 5? No, Yanis, if, as far as I am concerned, it should not. So number of score points roughly indicates the kind of workload, right? And workload for 0.75 is indeed 3 times higher than the rest of the homework, at least 3 times higher. There are 3 files on Brightspace. Are all of them for the first homework? Yes, homework is divided by packages. Let me reveal that there will be 10 homework problems. Then it is divided by 4 packages with certain deadlines. So it goes 3, 2, 3, 2. First package 3, homework exercises, them 2. Okay, you got it. Is the grade the average of the 3 HW? Each is 100 points. Let's see. We are not about the grade yet, but okay. Let me explain how does it go. If you do normal homework without bonuses, and if you do it completely, you got 200 score points. If you do some bonuses, you can get more. In any case, the maximum score which you can get for your homework is 200 points. And these 200 points contribute with a factor 0.15 to your final grade. Which means that, yeah, you got 1.5 of your final grade automatically if you completed your homework. If you complete only part of it, you got less. Fine. So let us switch to individual questions. Sir, no, let me remind. So if you're supposed to have questions now about this particular homework. Yeah? Number one, please don't ask questions about problems 2 and 3. Time will be to ask these questions, but not now. And raise your hand, and instructor will write in the chat. I will take care of you. To warn other instructors that they should not. There is an important point. When instructor has contacted you, please put your hand down. Otherwise, all instructors will contact you. Everything is clear? Okay. Let's make it a go. So Leon is raised hand. I will take care of Leon. Good. Problem number 3. And this is not joke anymore. It is really something resembling your actual exam problem. All right. So it becomes serious now. Let us see. We consider bosonic particles with spin S1 and mass M. So there's already plenty of particles. So we are in the subject of advanced quantum mechanics. It's not an exercise anymore. It's about actual system. Right. They can find in a big volume. So there are 3 possible spin projections for spin 2. That's why the operators are labeled as such, this wave vector. And in addition to this wave vector, there is alpha index, which can take 3 possible values. There was a typo in initial upload on the Brightspace, but I hope this typo was minor and didn't prevent you from looking what's going on. Right, so we have kinetic energy of the particles, although we did not write it explicitly. Yeah, particles with mass m. But in addition, we also have interaction, and that we write as follows. What we write as follows? Yeah, it is similar to the formulas which we use to derive the interactions for four fermions. And so it's the same for fermions, but just written as in a bit differently. It's product of two operators of density at opposite k, the com, and the com is a coefficient, which is eventually, what do you call it, Fourier transformation of two particle potential. Doesn't matter now. It's a real function. U is real, and it depends only on the modulus of Q. Density operator, you know what is this? It is defined. So if you write it in coordinate representation instead of Fourier representation, you got just two field operators in the same point. Fine. This is general formulation. So anytime you encounter general formulation, take time to read it carefully. Then the goes down. Well, we have implicitly assumed that there's some kinetic energy. There's no formula for that. First question is to write down the Hamiltonian corresponding to non-interacting particles. Good. So you write energies k squared something. Right. And again, it is some students might find it too simple and might be confused with that, but this is really simple. You just figure out what's the ground state of the system. And since the bosons, they like to be in the lower state. So eventually all the particles would go to this lower state. Right. Again, we have even stressed that this is trivial point, owing to big numbers of students who try to find something non-trivial in this point. Fine. Timur, what was your question precisely? Okay. So let us look at the next point. Again, perturbation theory comes into play. And first order perturbation correction. Right. And I want to get this in the limit of big numbers of particles. It's natural because I'm looking for the whole system of the particles. Right. And then there is kind of a rather explicit hint. Kind of proof check. The answer should be like this. And your task is to compute A, to give expression for A. Fine. Then there is a question which I have discussed a week ago. We need to figure out the states which are produced from the ground state by applying elements of the Hamiltonian to the initial state, ground state, whatever. We know what is ground state. We have established it in point A. Floris, it's a good idea, but that is not what we gonna do in the nearest future. Perhaps next year we can implement your idea. Okay. Fine. The resulting states, as it explained, have zero total momentum, and they correspond to two particles which are created with opposite momenta. Right? So again, as I explained a week ago, it's a crucial point. It's a simple point. One does have to apply the whole Hamiltonian. One has to apply elements of this Hamiltonian, but really figure out what are these states. And there are energies. You excite some particles, you pay energy for that, just make sure that you understand how much do you pay. Fine. You found the states, then you compute matrix elements between ground state and these states. Right. To remind, or better say to confuse you, there is a formula for second order correction for an arbitrary quantum system where A and B are arbitrary quantum states. For our system, arbitrary quantum states would be states with arbitrary numbers of bosons. Would be too complex. Fortunately, one doesn't have to sum up overall this multitude of states. One has to restrict yourself to the states which have been found under point C. Right, good. Then there's a formula of summation. We know how to go from summation to integration. So in the end of the round, the answer should look like this. Again, it is a rather huge hint. And there is a coefficient b in front of it. You've got to write it down. And then answer if the degeneracy with respect to different numbers of spin components is preserved in this case. Good. And bonus point, I don't want to discuss it now. And again, bonus is bonus. Fine. So let me look at the chart. Are there any questions about this formulation? As I said, it's already very close to what you get during examination, so. I don't see any questions. Fine. And then we just go to individual questions, please.